So consider something like this. Let's say that you've got some variable x1 and another variable x2. And in the placebo and drug kind of example, we might have that. And let's say you've got some numbers, whatever, we'll make something up, 100, 90, 75, 82, and so forth. Let's say we have n one of these. And then for x2, we had a certain group of people that took the drug, and they have slightly different numbers. But these are different people, and that's kind of the critical part here. So let's say this person has 99, 102, 87, and 130, and 150, and so forth. And there were n2 of these. Now, under the traditional hypothesis testing kind of setup, x1 and x2 are independent. And every single observation here, like let's say this person right here, in no sense does this particular person who received the placebo match up with any one particular person in this second column. So it's not like the row is the unit of observation. Every particular cell is an independent, different unit of observation. That's the traditional way of doing this. Today, we're going to look at matched samples. And in a matched sample, rather than having two really distinct samples, one of size n1 and one of size n2, instead what we're going to have is, let's say, x1 and x2. But here, x1 might be a pre and one might be a post. Like, let's say we wanted to know what people's weight was before and after they started exercising. There's no control group here. It's just you have pre and post. And maybe one person weighed 180 pounds and then put on some muscle and went up to 190. Someone else was at 190, lost some weight. Another person stayed the same. Let's say another person lost 100 pounds. In this matched samples case, it's not like we have n1 of these and n2 of these. Each observation is a particular group. A pre and a post represents one particular person. And likely, let's say, this is person number 4. And so we just have n of these. In the first situation, these guys didn't match up. 100 didn't match up with 99. So we could have taken our data set and shuffled it around. We could have taken x1 and kept it the same and shuffled x2. So let me switch colors here. So we could have moved 99 down and 102 down and the 87 down and the 130 down, and then put this 150 up here. And we'd still get the same thing because, well, the average of x2 hasn't changed, and certainly the average of x1 didn't change, and we were just comparing these two things. In this particular lecture, instead, what we have is a matched pair. 190 has to go with 170 because this represents a particular person who lost 20 pounds. This represents a particular person who lost 100 pounds. We couldn't reshuffle this. We couldn't pull the same trick and make this guy 190, and make this guy 170, and make this guy 200, and then this, move that up, the 180, and say, oh, look, person 1 didn't lose any weight, right? That's not how this particular example works. You can't reshuffle because the x's, the x1s, and the x2s form a matched pair. Okay, so what this means then is that we're going to have to just kind of tweak our test statistics and our confidence intervals to reflect this particular fact, one of which is we have n observations rather than n1 and n2 observations. So let's see how this all works. Again, before, when we just had a single sample, so this is like going way back, like several videos, if all we had was just one column of data, and we had n observations of these, so we had some distribution of x's, don't even call them x1s. These are x's. And if we were to take a particular sample and calculate the mean, I mean, we don't know what our samples would be, but they would likely, well, they would have a much smaller standard deviation, and because it's called the standard error and it's a little different, it would be unbiased and so forth. And this would be our distribution of possible sample averages. We take one sample of size n, and it's, you know, one particular sample out of the universe of possible samples that we could have taken. And then we want to know how likely was this guy. So we formed a test statistic. We took our sample statistic, the particular value of our sample average. We subtract off the hypothesized mean, what we think it might have come from. This is usually represented in our null hypothesis. And then we divide by the standard error. The standard error was sigma. That's the standard deviation of x divided by the square root of the sample size, so however many observations we had. So that's what life was like when we just had a single sample. Now, instead, we have a matched sample, so we've got something that's a little bit different. Now, not only do we have an x1, now we have an x2 that goes along with it. And these two go together, these two go together, and so forth. Now, we still want to compare pre and post, or x1 and x2. So we still want to know what the average is for pre and the average was for post. Let's say the weight before you started exercising and the weight after you started exercising. So calculate the difference between those, the average weight before and the average weight after. That's this guy here. Notice that is a sample statistic we could calculate from our data. And then we subtract off the hypothesized mean. Now maybe somebody says, exercise does nothing, in which case the hypothesized mean difference would be 0. But it could be any number. Right? So you subtract off what your null hypothesis says the difference between the means might be. And then we have to divide by the standard error. Before it was the standard deviation of x. Now it's the standard deviation of x1 minus x2. So standard deviation of x1 minus x2. And then we're just dividing by the square root of the sample size. And remember, we only have n observations. It's not like we had n1 of these and n2 of those. These are, the number of rows is the same in each of these two columns because they go together, they match up. So there really is not much of a difference in these test statistics. We have our sample statistic, we calculate, we subtract off the hypothesized mean, and we divide by the standard error. Now, when we were doing non-matched, like independent samples comparison of means, this standard error thing sometimes got a little bit hairy. We had to take into account different sample sizes and different standard deviations and all that good stuff. In this case, this one is not terribly difficult. We still need to know, like, what is the standard deviation between x1 and x2? And I'll have to show in a different video. I'll try to put a link. But if you're looking at the standard deviation between two variables, x1 and x2, even if they're subtracted, In fact, let's do the variance. The math there works better. The variance of some random variable that's the difference of another two random variables, that's equal to the variance of the first plus the variance of the second minus the covariance between them. But the way this thing is set up, there is no covariance between them. So that part cancels out. And then we just take the square root. So we take the square root of the variance there, square root over there. And so we get the standard deviation of the difference is equal to the square root of the variances of x1 and x2. And that's what we put here. So this denominator then becomes, in fact, let's just rewrite this whole thing. Our test statistic is the observed difference between the two means minus the hypothesized difference between the two means divided by the standard error. The standard error is now sigma x1, sigma x2, these are going to be variances, and then we take the square root of that whole thing. Now let's just say, just for the sake of argument, that x2 turns out was nothing but a bunch of zeros. Okay, then this whole thing just collapses back to our original test statistic. This would just be x bar minus, well, the average of a bunch of zeros is just 0. The hypothesized mean of a bunch of zeros better be 0 as well. So we just have that in the numerator. The variance of something that's a bunch of zeros, that's 0 too, because they don't vary at all. It's the same number. So that variance is 0. And so sigma squared x plus 0, you can ignore the plus 0, divided by n. Take the square root of that guy. Square root of a sigma squared is just sigma, leaving us with our familiar test statistic. So you can see that the original case where we just had a single sample is really just a special case of this more general formula when our second variable basically doesn't vary at all. At any rate, this is our test statistic. Not too bad. It's easiest to learn by an example, not by deriving equations. So let's work through an example. This is made up, but this is plausible. Your dean wants to know whether your students actually learn anything in their classes. Let's say they're taking an economics class. And he suggests that what you do is you hand out a pre-test at the very beginning, first day of class, before they've had a chance to listen to the professor's wisdom. And however they do, they do. And then you want to ask the same students economics questions at the end of the course. And so you've got a pre and a post. And each observation, so we have pre and post. A particular student might have scored a 60 and then, it might have gone up to 70. But that's one particular observation. And maybe somebody else, did pretty well and actually slightly went down. It's possible. But you can't rearrange the 70 and the 69, these two, because they match up together. Each pair makes up an observation. So we've got our matched pairs kind of situation going on. Okay, so you've given a pre-test, you've given a post-test, and your dean wants to know whether the professor is able to actually teach economics well enough that they raise test scores by 10 points or more, so by at least 10 points. And let's say you're going to be testing at the 5% significance level. So what's our research hypothesis, or our alternative hypothesis? Well, that's what we secretly want to show. Basically, what we want is that scores post, so the average of the post scores, minus the average of the pre-scores is at least 10-point difference. Now, the logical complement of that is the null hypothesis, and that just says that the average post minus the average pre is less than or equal to 10. So, in other words, that the professor doesn't increase scores by 10%, maybe even by, nothing, maybe even by, who knows, a negative number. Maybe the class does damage. Certainly wouldn't be the first time. So, all right, so we've set up our problem, and now we need to collect some data. So let's say that we did that, and we've got pre-test and post-test, and we gave our students on the first day of class a quiz, and they got a 64.4, but gave it to them at the end, 120 students, and they scored a 75. So this is looking pretty good. The average is actually a little bit more than 10 points better, but what's the chances that it could have gotten 10 points better, at least 10 points better, by random luck? So our test statistic is just like before. We have a sample difference minus a hypothesized difference, and then you divide by the standard error. Okay, so here we would have x1 minus x2, right, minus the hypothesized mean, and then divide by, again, this is our standard error. It's the standard deviation of the difference between the two samples. We got x1 and x2. You can just calculate the difference between these guys. That'll be a new variable, and then just calculate the standard deviation of that difference, and then divide by the square root of n. So yeah, let me just write that again. You've got x1, you've got x2. Let's say that one person scored I forget what numbers I used before. Someone scored a 70, then they scored an 80. Someone scored a 72, they went up to a 79, and so forth. The difference here, which let's call this x1 minus x2. Well, here that difference is negative 10. Here this difference is negative 7, and so forth. And then you could just calculate, you've got this sample now of this column of data. You could just calculate the standard deviation of this data set. So you could do that here. Now, x1 minus x2, that brings up an important point about implementing this in Excel. Excel has got a couple of quirks. We have many quirks, but two that are relevant here. The first is that if we're going to hypothesize a particular difference, that difference has to be a positive number. All right, so must be positive. But if we're doing pre minus post, that difference is probably going to be negative, assuming that the class actually does something good. So that's one particular peculiarity here of Excel, is this thing has to be a positive number. And the other thing is when we're entering our data into the data analysis tool pack, which we'll see in a second, whichever variable we list as variable 1, right, so we'll have x1 and some variable x2, it's always going to do x1 minus x2. And that might actually give you the negative number, right? If we're doing pre minus post, you've got a smaller number minus a bigger number. So if we could do this whole problem in Excel, we're just going to have to let what we call x1 be our post variable. The variable we list second is going to be our pre variable, which is a little, I think, backwards, but we got to work with Excel. Okay, so that's pretty much it. Let's switch over to Excel and try this out. Okay, so we've got Excel open. We've got a bunch of data. We have scores for our pre-test, scores for our end of semester post-test. We have a whole bunch of these. We have, well, let's scroll all the way down. We've got 120, observations on each. Row 1 is the label there. And we just go through our usual thing of using our data analysis toolpack. If you haven't installed your data analysis toolpack, I'm going to try to put a link somewhere up on top just to show you how to install that. But if you have installed it, you should be able to find it under Data. And then for me, it's all the way to the right there, Data Analysis. And click on that. And it brings us up to this little window here. We just need to scroll down towards the t-tests. And then here's our matched sample. Excel calls this a paired sample. That's another common way of expressing this. So click on that, and you get something that should look a little familiar. You got to tell it what your two variables are. And remember now that it's going to do pre minus post. It's going to do the variable 1 minus variable 2. But we want this difference to be 10. It's got to be a positive number. So really, if we're going to do a minus, this variable minus that variable, the first variable that we list has to be post. So let's highlight this guy. And we do that. And then we need to do this for our second variable. So A1 through A121. That first cell is a label. So we want to make sure we checked off label. I think we said alpha for this example is going to be 5%. And now we just got to tell it where to spit out all this wonderful information it's going to calculate. So let's click on output range and then minimize this thing, and we're going to tell it we want all that good information right there. And then expand that again and click OK. And now we get some output out of Stata, out of Excel. All right. So let's clean this up a little bit. We don't need all these decimals. Let's get rid of some of those. And some things we're not going to use. We're not going to use Pearson correlation. We're not going to use p-values. And this is a one-sided test, so we may as well get rid of those last two, the two-tailed test stuff. We have all the information now that we need. We've got a test statistic and we have a critical value. So let's just take note of that. Our critical value is 166 and our test stat is 491. So 166 and 491. So our test statistic was here. 166, that was our test statistic. And our critical value, our critical value was 166. And our test statistic was something else, was 4 or something, wasn't it? 491. So man, that test statistic is way out here. Which would be most definitely in the rejection region. Where you would reject the null hypothesis. All right, well that's fantastic because that's what we want. We wanted to prove that our class actually did improve learning by at least 10 points. And so we can conclude that it did. Now, just to summarize, what was our null hypothesis? It was that post minus pre is less than or equal to 10. Our alternative hypothesis was that post minus pre is bigger than 10. We've just rejected the null. So, which means we get to conclude the alternative. We have sufficient evidence to reject the null hypothesis. What's left? The alternative hypothesis, that post is at least 10 units more than the pre. So the professor is going to be really happy. The dean is going to be really happy. The professor deserves a raise. All right, so that's it. Thanks for listening, and I'll catch you next time. Bye-bye.